Welcome everyone. In this video we are going to use linear drag to find a formula for velocity as a function of time. So let's draw a drawing first. Our object will be represented by a dot. It will be moving upwards. So the velocity is upwards. And I'm going to choose the upward direction as positive and the downward direction as negative. Now, what will be the forces that act on our object? There will be mg, of course, the force of gravity pulling downward. There will be kv, and kv here is the drag force. It is linear drag because, as you can see, v is just v. It isn't squared, it isn't cubed, it is just v, and we have k, a proportionality constant, a positive constant. So this is the picture basically. Now, as I said, we want to mainly find v as a function of time. So how can we start? How can we start? Well, the best way to start is by writing the net force. So we will say F net is equal to, using Newton's second law, which I proved in a previous video. You can find it from the cards right now, also from the descriptions part. This is equal to mass times the acceleration. Now, F net in this case is going to be minus mg minus kv. And why do I put the minus? Well, because I chose downwards as the negative direction. That's the only reason for the negative sign. This is equal to mass, and instead of acceleration, I will write the time derivative of velocity because that is the definition of acceleration. Now we have this, and I will actually factor out a negative on the left, so we will have this. Just check my math that this is in fact correct. I will put the negative on the other side so that we have this. Alright, so far so good. Now I want to have dv and v on the same side. And a way to do that is as follows. I will multiply both sides by dt and divide by this guy. So I will have dt is equal to minus m dv divided by mg plus kv. Alright? Here, in order to solve this, I will assign a variable for mg plus kv. I will use u substitution. So I will say u is defined to be mg plus kv. If I take the derivative with respect to v on both sides, du by dv is going to be equal to, mg is a constant, kv will give k. So we see that dv is equal to du divided by k. Okay? Now I will substitute this. This is very important. So we will have dt is equal to negative m. Here, instead of dv, we will substitute du divided by k. So we have du divided by k, and this part, mg plus kv, well, we defined it to be u. So we will just put u. And from this, I will continue on the new page. So what did we have? We have dt. Now I'm going to multiply both sides by k and divide by negative m to get, let's see, what do we get? Negative k divided by m dt, right? Yes, that is correct. Is equal to du divided by u. Cool? Now I want to take the integral on both sides. So let's do that. We will have the integral. On the left, it will start from 0, go to any time t. On the right, we have u. So it isn't really obvious what the boundary should be, but we don't in fact care. So let's just call it u1 and u2. And you will see why we don't care that much, okay? So on the left, we will basically have, since negative k divided by m is a constant, the integral of dt from 0 to t will give us t, which means we will have negative km times t is equal to, what is the integral of du by u? It is ln absolute value of u. And we will have the boundaries u2 and u1. You can see that this is correct because if you take the derivative of ln x, you get 1 over x. Alright? And the absolute value simply means that the argument can't be negative. Ln is not defined for numbers that are less than 0. And it isn't even defined for 0 as well. Alright, from this, I will now switch back to the initial quantities that we started with. I mean that instead of u, I will substitute. We have ln, absolute value. What was u? Right here, it is mg plus kv. Let's just substitute that, mg plus kv. For the boundaries now, 4 times 0, we will have an initial velocity, v naught. For time t, we will have the general function of velocity that we are trying to find, which is v of t. Alright? And I'm just going to write this as v just to keep it short. That is the only reason behind this action. So we will have, let's continue it here, we will have, and also notice this, mg plus kv is always positive, so we don't even need the absolute value, we can get rid of it. We have ln mg plus kv, I am substituting the boundaries, minus, this is by the fundamental theorem of calculus, then we have ln mg plus k, v naught this time, I substituted the boundaries, and we can combine this under one logarithm as follows, ln mg plus kv divided by mg plus kv naught. Alright, now if I raise both sides to the power of e like this, e and e here, on the right, so from this part, we will get the argument of ln, because this is the definition of e and ln. They are inverse functions, they give back the argument. Which means we have mg plus kv divided by mg plus kv naught is equal to this part, which is e raised to the power of negative km t. Cool? Remember that we are finding v, we are trying to find v, so let's just solve this equation for v. When we do that, we have, let's see, we have, should I continue this on a new page? Well, why not? We can. mg plus kv is equal to mg plus kv naught. Let me just write it quickly. Alright, this is what we have. I just multiplied by this denominator to get rid of it. So we got this result. And now, since we are solving for this guy v, I am going to subtract mg from both sides and divide by k afterwards, which will give us, and check my math please, just stop the video and make sure that you are able to follow what is going on. This is equal to, we will have mg plus k v naught. Let me just write it and then explain. Alright, this is basically what we get. Now we can factor out some things to make this look nicer, which I will do actually. So we have mg times the e term here, which means if we factor out an mg, we can have e raised to the power of negative kmt minus 1. This is divided by k. And also the other term, k v naught e raised to the power of negative km t divided by k. This is also there. And we see k's cancel. Hooray, that is always nice. To leave us with the final result. That is v naught e raised to the power of negative k divided by mt plus mg divided by k e raised to the power of k over mt minus 1. And this is our final result. You can check that this equation makes sense by substituting 0 for t. When you do that, what happens? The first term will give you v naught plus the second this will be 1. 1 minus 1 will give you 0. So you will get v naught, which is the initial velocity. So it makes sense for the time equals 0 case. Also, another side note which is quite important, mg divided by k is called the terminal velocity, because this is the velocity that the object will reach if there is sufficient time. Okay, and when does that happen? Well, that happens when time goes to infinity. When time goes to infinity, the first term cancels, and the second term, well, this goes to 0, so we get negative mg divided by k. And why is it negative, you might be asking? Well, because it is downwards. The terminal velocity is achieved when the object is moving downwards. That's why we have the negative. And I remind you, we chose downwards as the negative direction. Alright, this is important. And one last thing, actually, if we graph this guy, oops, that's not how I want them. Let me do it one more time. If we graph time and velocity like this, we know we will start at an initial value and end at a terminal velocity. The graph will basically look like this. As you can see, as time goes to infinity, we approach vt, so there is a horizontal asymptote at vt, the terminal velocity. Alright, and you could in fact figure this point where it crosses the t-axis. This would be the turning point where maximum height occurs. And we can in fact do this in a future video. But this is it for this video. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.